Okay, so remember what we are doing. We're talking about convergence of sequences, right? Convergence of sequences, which is kind of similar to convergence of convergence of functions, right? Limits of functions. So let's just remind ourselves what it means for a sequence to converge to some. So we are right in some metric space, right? So you have some sequence in some metric space. You have some sequence in a metric space, and we say that that sequence converges. What does that mean? This means what? Okay, so everybody take the half a minute and write down what that means, just to make sure that you do know it, because if you don't know that, then, well, then we need to remind you of it. Dylan.
Wait, never mind.
What?
Wait, sorry, never mind.
Okay. I'm asking you to write it down, actually. Maybe you didn't hear that. Take a half a minute and write down what this means. Don't worry, your brains aren't here yet. That's all right. Okay, can anybody tell me what this means? What does this mean? What's the formal definition first off, right? What's the formal definition, Keisha?
So A and converges to P when there exists in capital N such that when epsilon greater than 0, the distance between A and AI and P is less than epsilon.
So let me write this down. If there exists a capital N such that
for any epsilon greater than 0, the distance between A sub I and P is less than epsilon for I greater than N.
Okay. So this is not quite right. What this would say is something like let me say it this way. So can anyone see what's wrong? What needs to be rearranged about this? Other than the regulars, Dylan and Salman, you guys are out. Anybody see what needs to be fixed about this? Yes, James.
Don't we need the total sum they have? They have just been the AI Never mind. I don't know.
Okay, that's all right. So what's wrong about this is the order. Actually, you got it kind of out of order. It should be if for any epsilon there exists an n such that this happens. Okay. So it's sort of like saying, let me say it this way. If you said it this way, it's sort of like saying, so it's sort of like saying, if in the correct order, it's yes, for any epsilon greater than 0, there exists an n, and this n depends on the epsilon, right? There exists an n dependent on epsilon, such that whenever you're past that n, the distance between a sub n and p is less than epsilon. Okay, so that's a little bit different from saying, that's actually significantly different from saying if there's an n such that for any epsilon this works. Okay, this is like saying, given any person, there's somebody who's going to be friends with that person. Okay, let me say it that way. Like given any human being, epsilon is a human being. Any human being, it has a friend n. Okay, there's going to be somebody who's a friend of that epsilon. Everybody's going to have a friend somewhere in the world. Okay, this would be saying that there's a person who's friends with everybody in the world. right? That's the difference here, right? This is saying there's this guy who is just, for any epsilon, it works for all of those guys, right? This person is like, just, completely, has no standards to differentiate. Okay, like, I'm willing to be friends with everything. Okay, and this one is kind of different. Like, for every person, there's going to be somebody who works with that person. Okay, so yeah, watch out. This is dangerous. You got to make sure that the logic is this way. Okay. So yeah, that's what convergence means. So in other words, you have some sequence, and it converges to some point. To some point P means that given any epsilon neighborhood, right? So whatever epsilon neighborhood you have, there's a time past which everybody's inside that epsilon neighborhood. Okay. So the other one would be, right, there's a time past which for every epsilon neighborhood you're inside there, right? That would actually mean there's a time past which everything is constant. Okay, that's quite different. That's actually too strong a statement. As you can see, this statement in terms of the friends is much stronger than this. Right? It's not just that everybody has a friend, but there's somebody who works for everybody, right? This actually does imply this, right? But it's a bit too strong. It's actually way too strong. Okay. So today we're going to be talking about 3 ideas: subsequences, Cauchy sequences, and diameters, I guess. The main idea is something called Cauchy sequences. Okay, and this is kind of related to something that people were pointing out in the questions. Some people were talking about, well, look, if we look at something like 1, 1/2, 1/3, 1/4, 1/5, blah blah blah, right? If we are in 0 infinity, does that converge? Does that converge? No, it doesn't count as converging because there's no point that it converges to in 0 infinity, right? So it does not converge, right? So it diverges in 0 infinity. Okay. Even though you know that there's this point 0, right, that it converges to, okay? But that point's not in your space. Okay, so this is sort of like, Cauchy sequence is sort of like convergent sequences which you think should converge. Okay, like this sequence you think, well, this ought to converge. It's true that the point is missing, but isn't this still a convergent sequence? It's not a convergent sequence, but it is what's called a Cauchy sequence. Okay, right? It's not. So it's sort of like. So it's no, this isn't convergent, but this kind of sequence is Cauchy. Okay. Well, we'll get to that in a minute. So before we get there, we're going to start with some simple idea about a subsequence. Okay. So here's the definition. Right. You have a sequence given a sequence. So P sub n, a sequence. In some metric space, of course. Okay. And let n sub k be a strictly increasing sequence in n. Okay, a strictly increasing sequence of natural numbers. Like 1, 2, 4, 6, 8, whatever. Right, so some strictly increasing sequence in n. Then we call the sequence P sub n sub k a subsequence of P sub n. Okay, so here the index in the original sequence, what's advancing is n, right? Here, what's advancing is k, right? Your index is k. right? So like, if I have some sequence, p sub n being, say, 1 over 2 to the n, right? That's, of course, things like 1, 1/2, 1/3, etc. Actually, let's start from 1/2, just to make it straightforward. Sorry, 1, 1/2, 1/4, 1/8, etc. Right? Then you see that if we take 1 over 2 to the 1 over 2 squared, 1 over 2 to the 4th, 1 over 2 to the 6th, 1 over 2 to the 8th, etc. Right? Then this is considered a subsequence of that sequence. Okay. Right. So this subsequence, whenever you have, right, and this subsequence corresponds to this strictly increasing sequence of natural numbers. Right. So whatever strictly increasing sequence of natural numbers you have, there's going to be a corresponding subsequence to that. Okay. Does that make sense? Anybody confused by that? Okay. So notice that 1, 2, 3, 4, 5, 6, blah, blah, blah. That's also a strictly increasing subsequence, right? So what, I'm sorry, that's also a strictly increasing sequence of natural numbers. What subsequence does that correspond to? So turn to somebody nearby and say, what's the corresponding sequence?
So that's okay though. What does
So we want to force extend this chosen.
Oh, okay, so the corresponding subsequence.
So this is your strictly increasing subsequence, it's a strictly increasing sequence, right? And then this is the subsequence corresponding to it. The subsequence corresponding to it. Let me.
Whatever we're indexing is that subsequence.
by definition?
Okay, so here's our sequence, right? And then you know what a subsequence is going to be, right? A subsequence is just going to be some selection, right? Some selection of these guys in increasing order, right? So this is just the mathematical way of saying that. It's saying that we're going to choose, right? This one is P1, this one is P2, this one is P3, P4. Whoops. Yeah. Oh, there's a 5 missing. 6, 7. Right. This one is P4, P5, et cetera, right? And we're just going to choose a subsequence is just going to be choosing a subsequence is equivalent to just choosing some increasing numbers here, right? Like over there, I choose 1, 2, 4, 6, 8, right? So that's the corresponding subsequence would be 1, 2, the first, second, fourth, sixth, and eighth, etc. Would be this subsequence, right? And if I had chosen 1, 2, 3, 4, 5, etc., just like all the natural numbers, well, that subsequence would just be the whole sequence, right? Okay, so that's the corresponding the subsequence corresponding to this is just going to be the whole sequence. So that's also a subsequence. I just wanted to point that out, right? That you can consider the whole sequence as a subsequence of itself. Yeah, bye.
Is it like a similar relationship with like sets and subsets? So like if a sequence is a set,
Yeah.
a subsequence is basically a subset. It can be proper or.
Yeah. You do have to worry that it's in order, but yeah, basically. Okay. So let me put up a statement. Let me put up a question here. If suppose we have let P sub n be a sequence. Suppose all subsequences of P sub n converge. Does P sub n converge? Does the whole sequence converge? Think about it for 10 seconds. Talk to somebody. Okay. Okay. So of course, as we just said, the sequence is itself a subsequence of itself, right? So if all subsequences converge, then it also converges, right? Because it itself is a subsequence of itself, right? So definitely that's true. So this is just like, let's wake you up a little bit slowly. Okay, so the answer is yes, right? Suppose all subsequences converge. Does the full sequence converge? Yes, right? So it's true that all subsequences converge. Converge implies that the full sequence converges. Okay, what about the opposite? If the full sequence converges, does every subsequence converge? Express an opinion to somebody nearby.
Or at greater than somehow. Or within epsilon of the final values.
That's not saying that.
Well, the subsequence at some point has to be index greater than.
Okay, what do people think? Yes or no?
Yes.
Yes, the answer is yes. And you can sort of do proof by picture. You say, well, look, you know, if the whole thing converges, that means that so let's say it converges to some p here. That means that given every epsilon, there's a time past which everybody's inside the epsilon neighborhood, right? Given any neighborhood, there's a time past which everybody's in the neighborhood. Okay, but now if that's true, however, right, if you consider a subsequence, you know that subsequence at some point is going to exceed that time, right? The subsequence's index at some point is going to get over that time, and so past that time for the subsequence, right, everybody's going to be inside the epsilon neighborhood, right? So that's the idea. Let me show you how to write it down formally, right? So suppose that Pn converges to P, right? Okay, and let Pnk be a subsequence of Pn. Okay, right. So this is a subsequence corresponding to some n sub k, right? So you've got this remember, so like n sub k then is your increasing sequence of indices. Right? Okay, so remember what we want to show. We want to show that given any epsilon, there exists a time. I'm going to call it k. I'm going to call it k just to, because it's the k that we're going to use for the index here. Right? This exists a time k such that if k is bigger than k, then the distance of P and k from P is smaller than epsilon. Right? That's what we want to show. Okay? Okay, that's what we want to show, right? I hope everybody's okay with that, right? Right. We want to show that there's a time past which if your index exceeds that time, then everybody's within epsilon of p, right? And so, so what do we know? We know if there exists an n such that if n exceeds n, then Pn, the distance of Pn from P is less than epsilon, right? That we know because since Pn converges to P, we know that the full sequence converges to P, so there's some time past which this happens, right? So just choose K so that K bigger than K forces n sub K to be bigger than n. Right? N sub K is strictly increasing, so it goes to infinity, right? So you know that it's going to jump, you know, the n sub K's are going to jump over the n bar eventually, right? So then K bigger than K forces nk to be bigger than n, which forces the distance between p sub n sub k and p to be smaller than epsilon as desired. Okay, so this is how you would take your intuition and then translate it into mathematical rigor, rigorous mathematical argument. Okay. Any questions about that? Okay. So that's convergence in terms of subsequences, right? So, right, if you know that the sequence converges, that's if and only if all the subsequences converge. Right? That's sometimes useful. Here is a theorem that relates, sort of brings compactness into this. So suppose we have a sequence in axiometric space. Okay. So here it is. If X is compact, then you're guaranteed a convergent subsequence. So you're guaranteed that there's going to be some subsequence of the p sub n that converges. Okay, so let me do kind of the simple version first. So let E denote the image of p sub n. Okay, so it's just the collection of the p sub n as a set, right? Right. It's basically the union of all these guys as sets. Right. So for example, right, you could have some p sub n being -1 to the n. So maybe p sub n is in R. Right? You have some sequence in R, and p sub n is just bouncing back and forth between -1 and 1. In that case, the image is just going to be those two outputs. Okay. So it's you're not right. In that case, the image just has 2 points. Right? Even though, of course, the sequence is infinite, the image of it is finite. Okay, so suppose E is finite. Okay, well, what happens in that case? Why are you guaranteed a convergent subsequence in that case? Josh,
Well, I mean, I watched the video.
you watched the video.
It's a bit of a pop-up.
Okay, so you can that's all right. You can tell me. You can tell me, and that will show that you understood it. You
It was a Pigeonhole Principle, you have sort of
Exactly.
numbers,
Yeah.
values like sort of in the range of different numbers points, so one of them has to be hidden
Exactly.
a number of times.
Yeah. So by the pigeonhole principle, right? By the pigeonhole principle, right? Pigeonhole principle tells you that, well, one of these values has to occur infinitely many times, right? So suppose there are only finitely many values, e1, e2, to em. Okay, right? Well, you know that one of these guys has to occur in your as an output of your sequence infinitely many times, right? Right? Because if each of them gets hit only finitely many times, then your sequence would be finite, right? Right? If each of these guys exists as an output finitely many times, well, there's only finitely many of them, and so that would mean that your sequence was finite, but your sequence is infinite. Okay, so you know that one of the e sub k must occur as a p sub n infinitely many times. Right. Right. So just create a sequence that takes on that value. So we can create a sequence p sub n sub k such that p sub n sub k equals p sub n sub I, such that p sub n sub I equals e sub k all the time. Right? So we just create something that takes on that value every single time, and definitely that's convergent, right? Because it's going to be e sub k, e sub k, e sub k, e sub k, e sub k. Okay. Everybody all right? Everybody all right? Okay, great. Okay, so that's the finite case, right? So now we do the infinite case. Suppose that the image is infinite, right? And now we've got an infinite subset. We've got an infinite subset of a compact set, right? So what do you know? What is that? You've got an infinite set sitting inside of a compact set. So that tells you, Dylan?
There's a finite number of neighbors to cover E. Like you could take like a finite number of points in E and have its neighborhood.
That's true. So yeah, certainly you could cover the whole set because of compactness, right? But that doesn't really take advantage of this thing here, right? Remember what we're trying to get for. What we're trying to go for. We're trying to show that there exists a convergent subsequence, right? So we've got our compact set. We've got infinitely many p sub n's, right? Some of them may be the same, but there's infinitely many different ones. Okay, and we're trying to show that there's a convergent subsequence, right? Eric?
Wasn't there like a theorem that says there would have to be a limit point?
Exactly. Yeah. So since x is compact, we know that there exists a limit point. Let's call it p of your sequence in x. Right? Okay. So that's good, right? You've got this limit point. You know that it's got this property that no matter what punctured neighborhood you take, there's going to be somebody inside there from your sequence, right? So we play the usual game. We're going to construct now we'll construct a sequence that converges to this P, right? So let's construct. We will construct a sequence P sub n sub k converging to P, right? So you kind of see how we're going to do. I hope you see how we're going to do it, right? You say like, pick, just let Pn1 be, say, the first one. Okay. So we're just going to take the first guy as P1, right? Now we want to find somebody else who's closer and whose number is higher, right? So what do you do, right? Since P is a limit point, we know that there exists infinitely many Pn inside the ball of radius distance of P1 to P around P. Right? We take the first one, right? That may not be the farthest one, right? There could be, P2 may be outside here, right? P2 could be outside, P3, whatever. Maybe P4 is over here. But what we know is that, given that distance, right, between these 2 points, we know that there's somebody, there's infinitely many of the P sub n inside here, right? So choose one whose index exceeds exceeds n1, right? Right. n1 is 1, so we're okay. We know we can do that, right? Right. That will be let n2 be the index. Right? Let n2 be that guy's index. So in this case, say we've got this P4 here. We know P4 is inside here. We're going to let n2 be 4. Okay, our n1 is 1. Our n2 here in this example will be 4. Okay, and you can see what's going to happen, right? Right? You just say, okay, and then wash and rinse and repeat, right? You just do the same thing, right? Let your epsilon be the distance from right? So next, let your epsilon be the distance from Pn2 to P. You know that there's somebody inside there. There's infinitely many guys inside there. So choose one whose index is bigger than n2, right? To ensure that you're getting an increasing sequence, right? We do have to ensure that we get an increasing sequence, right? Et cetera, et cetera. Okay, so by induction, I'm showing you how to do this, but basically, to do it formally, you do it by induction, right? You say, assume that you've got, a certain number of points, right? Then, et cetera, et cetera. Okay, so, right. Oh, actually, hold on one second. I'm a little bit wrong here, because actually, I want. Because I need to make sure that they definitely, the distance goes to 0. So let me take as my distance here the minimum of that and say 1 over 2 to the 2 to the 2 to the 1, right? 2 to the 1, and then the second time 1 over 2 to the 2, and the third time 1 over 2 to the 3, and so on and so forth, just to make sure that they do converge to this point. Because otherwise they could sort of like circle around or something. They could, it's not obvious that they're gonna, in fact, it's not even true that they would converge. It's not guaranteed that they would converge. Okay. Or maybe, let me make it a little cleaner. Okay. I do like this over 2. Right? Because then every time it gets multiplied by a half, and so it's going to be the same effect will happen. Right, so this guy would be half of the previous distance, but that was half of the distance before, and so on and so forth. That's better. Yes, Bayan.
I'm confused about why there would be infinitely many sequences inside that.
Infinitely many points. Infinitely many points.
But in
Sorry.
general, shouldn't it depend on the size of the sequence?
The sequence had, remember that you've got this infinite sequence, right? And that there are different values in there,
Oh,
right?
yeah, I missed that.
Right? There are infinitely many values. There are infinitely many output values for this sequence, right? So, you know, you've got your space, you've got your limit point, and you know that there's infinitely many p sub n, right? This being a limit point means that, you know, given any epsilon, there's infinitely many of those output values there. Sure. Any other questions? Jessica, you look like you have a question. Okay. Okay, let's get on with it. Okay. Right, so what we've just shown is that whenever you have a compact vector space, any sequence inside it must contain a convergent subsequence. Okay, so as a corollary, any bounded sequence in Euclidean space has a convergent subsequence. Right? I hope that makes sense. Right? Because if it's bounded, then you can find a K cell that contains it. Okay, that's basically what bounded means. And K cells are compact, so you know that it would be sitting inside of a compact set. Okay, so that's just a quick corollary that any bounded sequence in because of this, whenever you have a bounded sequence in Euclidean space, it's going to have a convergent subsequence. Okay, everybody all right? Okay, so I'm going to erase this. So we have space to get to the main idea for today, which is Cauchy sequences. Right, so this is sort of like distilling part of the notion of a convergent sequence, right? Convergent sequence basically has two parts, right? That there's a point that exists in the space, and there's a sequence that converges to it. So Cauchy sequence is sort of what happens if you remove that first part and just look at the second part of it. What does convergence mean if you're not worried about the point that it's converging to? Okay. Here's the definition. Okay. So again, we have some sequence in X metric space. Okay. So we say that this sequence is Cauchy after the great 18th century French analyst, Cauchy. We say it's Cauchy, or is a Cauchy sequence, if for all epsilon greater than 0, there exists an n, natural number n, such that whenever you have two values past that time, then the distance between those two values is smaller than epsilon. Okay, so you see the difference, right? What's the difference between this definition and the definition of converging to P, converging to a point? The difference is that there's no P, right? There is no point, right? There is no point. You don't care about a point existing. All you care about is that given any epsilon, the values get within epsilon of each other. Josh.
So just to sort of make sure I'm understanding correctly, would the example like you see this be like a sequence of like rational numbers approaching the square root of 2?
Yeah.
Okay.
Yeah, that's exactly, exactly. That would work, right? Because so like if we look at the rational like 1.4, 1.41, 1.41, 1.41, 42, et cetera, et cetera. So these guys, this is the beginning of the square root of 2, right? And you see that even though if we were in the rational numbers, there's nothing that they actually converge to. You see that they're actually getting closer to each other, right? That, if I say, oh, I'd like them to be within 0.1 of each other, right? You say, okay, well, I see that, past this point, past n equals 3, or actually I just could take n equals 2, as long as my, this is P1, P2, P3, P4, et cetera, right? I see that as long as n and m are bigger than 2, then everybody's within 1/10 of each other, right? And if for any value, you're going to be able to find some time past which all these guys are within that value of each other. Okay, yes, Sivan.
And so would an ordered field have the least overbound property if and only if all of its Cauchy sequences, all the Cauchy sequences are convergent sequences?
That actually is true. Yeah.
Okay.
Yeah. So that's yeah. That's another way of phrasing completeness, which we'll get to in a second. Okay. Okay. So okay. So this is what Cauchy means. So it'll turn out that Cauchy doesn't imply convergence. Right? In fact, we know that already, right? Because we just gave an example that showed that Cauchiness does not imply convergence. Right, because we have this Cauchy sequence, but in Q it doesn't converge, right? But the opposite is true. Convergence does imply Cauchiness, right? Why don't we do that right now? In fact, I was going to do it later, but why don't we just do that right now? So convergence does imply Cauchiness, and the picture is right. If you converge, that means that you can make everybody close to P, right? Well, if you can make everybody close to P, then you can make everybody close to each other. That's the end. That's basically the proof right there, right? You say, well, look, Cauchiness means you want to be able to make everybody within epsilon of each other. So what you do is you use the convergence to make everybody within epsilon over 2 of P. Then triangle inequality finishes the point. Okay. So maybe I'll write it out just to be careful. So convergent implies Cauchy, right? So just to be very slow about this, so we want to show that given, so let's say that we're dealing with a sequence piece of n. Given any epsilon, there exists a time such that if we are past that, if we have any two things that are past that time, then the distance between p sub n and p sub n is less than epsilon. Okay. Well, like we just said, since p sub n converges to some p, right? So since p sub n converges to p, we know there exists a time such that if you're past that time, then the distance from p sub k to p is less than epsilon over 2. Right? So since then, n and m being bigger than n would imply that the distance from p sub n to p sub m is less than, by triangle inequality, the distance from p sub n to p plus the distance from p to p sub n, which is less than 2 epsilon over 2. Okay, everybody all right? Right, but proof by picture, right? Here's p, right? Somebody gives you an epsilon. Somebody gives you an epsilon. You take the epsilon over 2 neighborhood. You know there's some time past which everybody past that time will be in the epsilon over 2 neighborhood. Well, if they're in the epsilon over 2 neighborhood, then they're within epsilon of each other. Right? If they're both within epsilon of 2 over of p, then you know that their distance from each other must be less than epsilon. Okay. Any questions? Any questions? No? Okay. Okay. So now we're going to sort of throw in an idea that won't be that crucial, but it's kind of useful. Okay, so here's a useful idea: is the notion of the diameter. Okay. So maybe before we get there, let me sort of throw in a small, even smaller idea: the notion of the tail of a sequence. Okay, the tail of the sequence. Okay, so if I have okay, so if I have some sequence p sub n, then I'm going to let e sub capital N denote everything past the nth time. So p sub n plus 1, p sub n plus 2, and so on and so forth. Okay, so it's all elements of the sequence past that time. Okay, that's the tail. That's the tail of the sequence. And starting from time n. Okay, so this is more of a notation than anything else. Okay. So let me get back over here to the notion of diameter. Okay, so here's the definition. So we have some metric space, and we have some subset of that metric space. Okay, so this E is just a subset. Okay, this E is just a subset of the metric space. Okay, And what we do is we let S be the collection of all distances between points in E. Okay, so this is just a collection of distances, right? So you have some set, and you take pairs of points, and you look at their distances, and you look at the collection of all distances. Okay, so it's just a collection of distances, right? Set of distances. Set of possible distances in E. Okay, then we define the diameter of S as the supremum of E. Supremum of S. Sorry, backwards. The diameter of E is the supremum of S. Okay, so you look at the least upper bound of this set of distances. It could be infinity, that's all right. And we call that thing the diameter of the set. So the diameter could be infinity. Okay. So okay, so I make the remark that a sequence is Cauchy if and only if the limit of the diameters of the tails goes to 0. Okay, let's remind ourselves what Cauchy means, right? So I just erased it, unfortunately. But remember that this is Cauchy means that given any epsilon, there exists a time such that if you exceed that time, then the distance between those corresponding points is smaller than epsilon, right? In other words, you can make, you can find a time past which everyone is within epsilon of each other, right? Right? What's that saying? There's a time past which the diameter of the tail is smaller than epsilon, right? That's the same thing, right? That, right? In terms of the diameter, that's saying given any epsilon, there's a time such that the diameter of the tail is smaller than epsilon, right? Given any epsilon, there's a time such that, in fact, past that, right? For k bigger than f. Okay. Okay, and so you can see that being Cauchy, so that gives it to you, right? If you're Cauchy, then the limit of the diameters of the tails is 0, right? That's what a limit being 0 means, right? The limit being 0, right? So, right, for the limit to be 0 means given any epsilon, we can find a time past which all these diameters are smaller in value than that epsilon, right? And that's exactly what Cauchiness is saying, right? And vice versa. So this is just this is just a sort of maybe a more geometric way of understanding what Cauchiness means. Kishan.
I'm confused by, if we take the limit as n goes to 0.
I'm sorry. Thank you. As usual, I'm reminded of one of my professors back at Princeton who, when we caught him in a mistake, he said, "Oh, so that's why you all look so stupid." Right. Yeah, he was a character. I'm sure I told this story in the videos, but Pomona College used to have an analyst. He retired a few years back. His name is Sandy Grabner. Yes.
I can wait after your story.
Okay. Yeah. So Sandy Grabner's son was David Grabner, who was at Princeton maybe a year or two ahead of me. And he and I were taking this class with John Conway. He's famous for the cellular automata called life. But that's as a mathematician, that's something he probably made up, in an afternoon or something. But that's as a mathematician, that's not what he's famous for. But in any case, that's an exaggeration. He probably spent more than an afternoon on it. I mean, he definitely spent more than an afternoon on it because there's a lot of mathematics that could come out of that cellular automata. In any case, so we were taking this representation theory class together, like a special topics course in representation theory. And at one point, Conway was putting something up, and Grammer said, "Professor Conway, what happened to Frame's rule?" And Conway looked at the board. It's like, yes. What happened to Frame's rule? Aren't you an annoying little man? Yeah, that's one of my favorite memories of Conway. In any way, sorry, someone.
So, given like the definition of Cauchy sequence,
Yeah.
is there like a strong relationship between the Cauchy sequence and maybe like its derivatives?
Derivatives, but we're in a metric space.
Or like, I guess like some notion of like difference, or because it seems like that it's saying that like the difference between two elements in a sequence should always be should always be decreasing or converge to zero.
Yeah, I guess you could characterize, well, possibly.
Okay.
Possibly. Okay. Let me give you a couple of facts. These are so let me put up a lemma. It's just some facts about the diameter. Okay, the first one is that, so if you have some set sitting inside your metric space, then the diameter of the closure equals the diameter of the set itself. Okay, right? That throwing in the limit points doesn't change the diameter. That's kind of believable, right? You probably expected that, right? And then the second, equally unimpressive, if you have a sequence of nested compact sets, then if the limit of the diameter of the case of n is 0, then the intersection of the case of n must be a single point. Okay. So these are, maybe not that impressive as facts. We'll use them in a minute to get something more important. Okay. Maybe the second one seems pretty clear to people, I hope. Right? You've got a sequence of nested compact sets. Right? Sequence of nested compact sets. right? So you've got these compact sets, right? They're sitting inside of each other, right? And so on and so forth, right? So you know that, for one thing, they satisfy the finite intersection property, right? Whenever you take finitely many of them, their intersection is just going to be the smallest guy, right? Right. So they satisfy this finite intersection property. Okay. So we know from way back when that their intersection is non-empty, right? You've got nested compact sets, satisfy them. You've got compact sets that satisfy the finite intersection property. So we know that their intersection is non-empty. So this one is pretty easy. So recall that that their intersection is non-empty since they satisfy the finite intersection property, which I'm just going to abbreviate as FIT. Okay. Right? And we know that the limit is 0. The limit of the diameter is 0. So it has to be a single point, right? Because if there were 2 points, then the diameter would not be 0. Okay, so that second fact is pretty straightforward. The first fact is also pretty straightforward. Right? Yeah. Right. So let's prove that. Okay. So proof of one. Proof of one. Okay. So it suffices to show that the diameter of E bar is less than or equal to the diameter of E. Right? Because the opposite direction is obvious. Right? So this direction is obvious because E bar contains E, so the diameter is definitely greater than or equal to. Right? So we don't need to worry about that. So it suffices to show this inequality. Okay, so let's see. So pick any 2 points, P and Q, in E bar. Okay, and choose an epsilon greater than 0. Choose an epsilon greater than 0. We know, right? We know there exists a P prime and a Q prime in E such that the distance between P and P prime is smaller than epsilon over 2, and the distance between Q and Q prime is smaller than epsilon over 2. Right? These guys are in E bar, so they're either in E themselves or they're limit points. Limit points of E, right? So in either case, if you're in E, then just choose your P prime to be yourself, right? Right? If you're a limit point of E, well, there's definitely going to be somebody within epsilon over 2 of you because you're a limit point, right? So we know that there's somebody within this distance of each other, right? So what does that tell us? That tells us that the distance between P and Q is smaller than or equal to the distance from P to P prime plus the distance from P prime to Q prime plus the distance from Q prime to Q. Right, by the triangle inequality. Right, we go from P to P prime to from P prime to Q, and then from Q prime to Q. Right? Okay. So that tells us that the distance from P to Q is less than or equal to the distance from P prime to Q plus epsilon. right? So what does that tell us, right? So this is less than or equal to the diameter of E plus epsilon. Right. Now let's take the least upper bound of these distances. So take the least upper bound, the supremum, over P and Q in E prime. That gives us that the diameter of E bar is less than or equal to the diameter of E plus epsilon. Right? But that was true for every epsilon. That's true for any epsilon. Our epsilon was arbitrary. Right? So let epsilon go to 0, and that gives us the result we want. Right? Okay, so. Right, you can see that this prevents the diameter of E bar from being strictly greater than the diameter of E. Right? If this diameter of E bar were strictly bigger than the diameter of E, well then you just choose an epsilon smaller than the difference. Right? Smaller than the difference, and that would give you a contradiction. Okay. Okay. In any case, here these are just some facts about about diameters. Okay. Let's see. Okay. So we've got 5 minutes. I think I can do it. So one last. Let me just introduce one definition first. So here's the definition. X a metric space if every Cauchy sequence converges in X, we call X complete. Okay, so for example, RK is complete. Okay, let me put up the last theorem that actually we don't quite have that yet. So let me put up the theorem that will give it to us. If X is a compact metric space, then X is complete. Okay. Okay. So we want to show that every Cauchy sequence converges here. Okay. So let P sub n be a Cauchy sequence. And let E sub capital N be the tail, right? So Pn plus 1 be the tail. Okay. Now, let's consider the closures of the E sub n. Okay, so right, we want to show, right? Our goal is to show. We want to show. No, sorry. sorry. We know, because it's Cauchy, we know that the limit of the diameters of these guys goes to 0, right? So just a reminder, we know that the limit of the diameters of the E sub n's is 0 as n goes to infinity. Okay. So now we're basically going to use the results of the lemma, right? These guys, if we look at the closures of these guys, they're closed subsets of a compact set. Right? If you're a closed subset of a compact set, then you are compact yourself, right? So each is compact, and they're nested. Right? They're nested, right? The earlier guys contain the later guys. Right? Because that relation holds true for the E sub n's themselves. Right? The E sub n's, every E sub n contains the later E sub n's. Okay, so they're compact, they're nested, and their diameter goes to 0. Right? So what do we know? We know that that the intersection of their closures is some point, is not empty. It's a single point in X. Okay. So now, given any epsilon greater than 0, choose an n naught such that if you're past that time, your diameter is smaller than epsilon. Okay. Then, for all little n bigger than n naught, we have that the distance from p sub n to p is less than epsilon. Right? So the p sub n converge to that p. Sorry, let me just take one minute. I'm sorry to hold you over, but let me just take 1 minute. So the proof is in 2 parts. Okay. The first part is to find this point P. Okay. We construct this, we find this point P that lies inside of X, and we do it using the lemma from before. Okay. The second part is to show that our sequence actually converges to that P. Right? Because we're trying to show that X is complete. Right? So we want to show that if you're a Cauchy sequence, then you converge to something in the space. Right? So we find something in the space, and then we make sure that we actually converge to that thing in the space. And the way we do it is we say, well, look, if you want my points to be within epsilon of p, all I have to do is find out the time when the diameter of the tail is smaller than epsilon. Right? The diameter of the tail being smaller than epsilon means that everybody in that tail is within epsilon of p. Right? P lies inside there. Right? So past that time, everybody's, the tail is smaller, the diameter of the tail is smaller than epsilon, so everybody must be within epsilon of p. Right? And so the sequence converges to p. Okay, sorry to keep you over. That's it. Tests.
Yep,
Sorry. Okay.